Okay, so let us begin the lecture. So today we are going to discuss the next topic in our progression through control theory. Let me just quickly place it in the row of topics that we have studied. So our first topic was how to transfer something to the state space. Okay, so we knew ordinary differential equations. First thing that we learned is how to place them into state space form with matrices. Okay. Second, we asked how to check stability of the systems in state space form. Okay, and that is through eigenvalues. Right. After that, we spent some time. And after that, we said that we can choose control that can stabilize the system. Okay. So we had system in the state space form. We check its stability through eigenvalues, and then we can choose control law such that closed loop system, so system where we substitute the control law inside the system, that closed loop system is stable, so it would have negative eigenvalues. All right, so that was the first 3 lectures. After that, we spent some time with transfer functions, then discrete systems. Now is the time to do the next logical step from those 3 first steps. And that is to give you a tool, like a viable practical tool that you can use to actually do this, to design control that makes the system stable. Okay. On the practical sessions, you already learned pole placement. Pole placement is a viable tool to find control law that makes the system stable. We will discuss at the end of the lecture the limitations of pole placement, but that was in the practical sessions, and we didn't study it in the lectures. So in the lectures, we will concentrate on a different approach, and that is LQR. LQR is such a popular tool for designing control theory. For designing control law, that for your linear systems, that basically it is, you can say, just like part of common vocabulary, okay, for people who work in this field. In practice, of course, you can argue what is actually used more often. Like someone would argue that PID tuning, according to manuals of how to tune single input, single output PID, is the most important practical tool for designing control law. That is outside of the scope of this course, but just so you know, PID tuning, that is one aspect. Pole placement, more classical, you could say more straightforward approach to design control law. Someone can argue that this is more popular, and LQR, maybe someone will argue that this is more popular. We're not trying to decide which one is more popular, which one is more influential. That is not very important for us. But just so you know, what we are studying is one of the pillars of control law design. So it is not just something. It's of extreme importance, for control theory. All right. And the key aspect of what I'm going to do here is to bring, for the first time, additional concept, and that is optimality. Before that, we were talking about control in terms of only one criteria, and that one criteria was stability. Okay. So far, we only wanted the system to be stable. For example, if the system has eigenvalues -10, we are happy because it is stable. If the system has eigenvalues -0.001, so 1 over 1 divided by 1,000 is a negative sign, and -10, we are still happy because it is still stable. Of course, you can understand that the second system would decay to 0 much slower than the first. So in fact, the second system will be performing worse if what we understand as worse is how fast the control error decays to 0. Right. So you can say that the two systems behave differently, and you can measure their performance somehow. and say that the first system is better than the other. Now, if you can clarify this measurement in terms of some mathematics, you can talk about optimality. So optimal system would be the one that behaves the best possible way given your circumstances. So given your limitations, given your what you care about, there will be some optimal way your system would behave. And this is much more strict than the notion of stability. Like there can be infinitely many ways to stabilize the system, but there would be usually only one way to make it optimal. Okay, so much more strict. And that's what we are going to talk about here. All right, let's begin. So first, we will try to understand where the notion of optimality comes in. Like how do we get it? That is not going to be used directly in your like when you apply LQR, but that will give you theoretical background, which I found in my practice to be extremely useful. So I would recommend you to try to understand what we are trying to do here. Okay, so first let us define dynamics as x dot equals to f of x and u. Okay, those standard state space dynamics. In this case, it is non-linear, so we don't say anything about linearity of the system yet. With initial conditions x of 0, okay, x of 0, maybe it is equal to x naught, something like this. Okay, so dynamics initial conditions, great. Now we will define control policy as u equals to pi of x and t. So here the reason why we suddenly introduce this new like we introduce two things. All right, first is a new term, control policy. Another one is new letter pi. Okay, so the reason is just to avoid some confusion. Okay, so I can say u equals to u of x and t. That is a typical abuse of notation that we use in math. But more correctly, when you say you have a function, like to call function one thing and to call the output something else, okay? So function and output are not usually the same thing. So let me just write it as we usually write. Usually we say u is equal to u of x, let's say, okay? So u is a function of x, that's how we say it. So here the abuse of notation comes in the fact that the output of the function and the function itself is denoted by the same letter, okay? Usually it doesn't matter because you have no chance of confusing the two. You don't have a chance to confuse the output of the function with the function itself, okay? So the function itself can be a cosine, for example. The output of the function for a given x can be, let's say, 0.7. So two different things. U is a cosine here, u is 0.7 here. Right? Two different things. Okay, now here, same thing can happen. And we would really like to differentiate between u, output, and p, like pi, the control policy. Now, why do we say control policy? Again, this is to avoid the same confusion. So classically, we call like this control input or just control, okay, u. And this we call control law, okay? So the law of how control is defined. But just to avoid, well, I mean, we call them the same thing so often, as in that somehow it just becomes dangerous in terms of being, you know, in terms of mistaking one for the other. We could have stuck to control law here, but I introduced control policy, and part of it is just so you don't, don't feel afraid when you encounter this next time in, let's say, like reinforcement learning or something like this, where they use control policy very typically. It doesn't matter. Control policy and control law is the same thing. It's just the way to reference pi. So the way you compute control, the function, not the output of the function. All right, so dynamical system and control policy. All right. So what would be, for example, a way to choose a different control policy in our familiar settings? So for example, let's say this is the control policy number one. There's a control policy number one, let's say. And here's the control policy number two. As long as K1 doesn't equal to K2, those are two different control policies. So like choosing gains, different gains will give you different control policy. Okay. Control policy is allowed to depend on time. And that would be typical for time varying systems. So or for the tracking control or something like this. So there's nothing surprising about T. But as long as we're talking about LTI, so linear time invariant systems, and what we're trying to solve is stabilizing the origin. So x equal to 0 is what we're trying to stabilize as a solution. As long as we do that, we would have p of x, usually, pi of x. If you want to review other options, I would suggest starting with looking at the lecture on control and trying to see how it would look like if we have try to stabilize a solution which is not at the origin. Okay. Now let us introduce next innovation. That is a cost function. Okay, it is a cost function. There's also additive cost function, not just a cost, additive cost. What do I mean by additive? Well, additive refers to this integral here. So this integral is, if you remember calculus, integral is a limit of a sum. So you have a sum, infinite sum of components, or like, how should I put it? I think you probably understand what I mean. But if you think of an integral as the area under the graph of function, you slice this area under the graph with vertical lines. You increase the number of vertical lines infinitely, and the sum as limit approaches infinity becomes integral. So is a sum, basically the sum of those thin slices. So this is why we call it additive. In discrete case, this would be literally a sum. In discrete case, it would be literally a sum. In continuous time case, it is an integral. All right. Now, here what we have is a policy. And here we have initial condition x0. Okay. So cost depends on initial conditions and the control policy. And what it integrates is cost, which is a function of x and u. Okay. Now let us try to understand what's going on here. So first of all, this cost is what we call instantaneous cost. So we look at the pair x and u, and we decide how much we want to punish it. Let's say our ideal case is when x and u are equal to 0. Let's say that this is our ideal case. X and u are equal to 0. Then we might punish them for being not 0. Like, for example, x squared plus u squared would be an example of such a cost. Can be anything else. All we ask for is that it is instantaneous. So it depends only on current x, current y, or current u. All right. And now this is the initial condition, x of 0. Now notice that here we have initial condition instead of x of t. Or why? Well, because if you know control policy and you know initial condition, you can solve Cauchy problem to find x of t. So cost doesn't depend actually on x of t. It depends only on the initial condition, because x of t itself depends on the initial condition and control policy. So you have a control policy, you already know what x of t will be. So the cost only depends on the initial condition and control policy, which kind of makes sense. You can say my cost will depend on from where I start and how I drive my road. All right. Now let us try to decide to talk about the optimal cost, G star. Star will denote optimality for this lecture. So there's optimal, lowest possible cost. Okay. So G star now will only depend on x of 0. And what is it equal to? Well, it is equal to infimum over all control policies, so minimum over all possible control policies, over the original cost j of x0 pi of xt. So notice what happens here is we take all possible costs from a single initial position with all possible control policies, and we find the smallest possible cost for all given like different control policies. So we find control policies that delivers the smallest possible cost, and that would be the optimal cost for x0. Okay. So given given all possible costs, this would be the small for all possible control policies, but a single initial condition. This would be the optimal one for this initial condition. Okay. And the control that makes it possible, is control policy is pi star of x and t. Okay. So is the pi star of x and t. So the control policy that makes it possible is pi star. We call it pi star. Is the optimal control policy. Okay. So just to reiterate, we have a control policy which is additive. It is an integral over instantaneous cost from 0 to infinity. Depends on initial conditions and control. We have optimal control policy, which no longer depends on control, because we, out of all possible controls, we've chosen the one that delivers the minimum to the cost. So it only depends on initial conditions. Okay. Now, with this, what we can formulate is Hamilton-Jacobi-Bellman equation. So Hamilton-Jacobi-Bellman equation. We call it HJB. Is a famous equation, and the types of this equation are used in reinforcement learning. Types of the equation are used in optical control. Is just important piece of mathematics. It has direct connections with dynamic programming in discrete version of this control, with Bellman principle of optimality that is used, I believe, in reinforcement learning. So don't feel like this is useless. This is actually, if you're going to study one of those fields for your advancement later, you might find it useful to understand how it works in this context. So, right, Hamilton-Jacobi-Bellman equation. So what it is a minimum over u, okay, minimum of u of instantaneous cost plus partial derivative of optimal cost with respect to x times the dynamics of the system. And this whole thing, this minimum over u for this guy is equal to 0. Okay. So you may find this random. You'll be like, at least that's what's my impression. When you look at it, you'll say, okay, instantaneous cost. Okay, For some reason, we care about it, even though it is instantaneous y. Okay. Then optimal control policy here, or optimal cost, sorry, here, partial derivative times dynamics, all look very strange. But if you think about it, this whole thing here is looks a lot like a time derivative of the cost function. Time derivative of the cost function. Okay. In fact, you can say time derivative of the optimal cost function. Now let us see why. Let's look here. So if we're trying to take time derivative of this guy, what we'll have is using chain rule. What we would say is time derivative of j with respect to x. And here, let me just say with respect to x, like instead of x0, I will just use x. Okay. So with respect to x, it would be dj dx dt, but dx dt is of course f. Okay, dx dt is f of x. Okay, so time derivative for this guy using chain rule would have a first component is dx dj dx dt. So dj dx f of x. So this is how we get this component dj dx f of x. Okay, that's partial derivative. Now the second component will be partial derivative with respect to time. Now partial derivative with respect to time would be look at what this guy is equal to. It is a time integral. So partial derivative with respect to time would be just j of x and u. That's it. That's it. So partial derivative with respect to time would become j of x and u. So this component. And partial derivative with respect to x times x dot is this component. So this you can interpret it as x dot, like full time derivative. This mean over u, you can interpret as coming directly from the fact that we are talking about optimal cost, which is infimum over j, right? So we didn't just work with j, we worked with infimum over j. Okay. And we set it equal to 0. Right. Now, what you can think, like yet another way to think about it, is to say that optimal control, optimal cost is going to be bigger as long as you stray away from optimality. So the cost will be bigger as long as you go away from optimality. So optimal cost is always the smallest possible. So any time you stray away from the optimality, you go uphill. So you can kind of think of it as this relation, right? So whenever you have a situation where you are at the bottom of a hill, when anytime you do anything, you go uphill, your derivative at this point would be 0. Okay. So this is the intuition maybe for the 0. All right, that is not a derivation. That is just intuition. Like at least for me, when I first saw it, I found it difficult to wrap my head around this strange combination. This guy, and even this. So I'm trying to give you like a way you can at least feel comfortable with those things. I'm not giving you derivation here, and unfortunately, derivation of this equation is actually difficult to find. People usually don't derive Hamilton-Jacobi-Bellman equation in textbooks that are ones that I read. So it's unfortunate. All right. So this is Hamilton-Jacobi-Bellman equation, and as long as this condition holds, the control policy is optimal. the control policy U that you found is optimal. And this is true for nonlinear systems, not just linear. So any control policy that you find, if you want to check if it is optimal with respect to your cost, just plug it into this equation. And if it holds, then great, like you found correct control law. Of course, the problem is that it will be difficult to actually check in practice because of this mean over U. But you know, theoretically speaking, you could do that. So this is an equation, and this is the condition of optimality. Now, we can use it to find control law like this. You can say optimal control law is equal to arg mean over U for this guy. Okay. And remember, this guy should be equal to 0 for this arg mean. So if this condition holds, condition 5 holds, then optimal control policy can be found as arg mean over U. Okay, fair enough. So far, it just looks interesting, but it is unclear if it has practical significance. So let's try to get to practice. So for our practice, we are very humble. We use LTI systems, continuous time LTI. X dot equals to AX plus BU. Okay. Let us use the quadratic cost. So our instantaneous cost will be quadratic. What does it mean? Well, we'll use components of cost X, QX, and URU. So this is X times Q times X is a quadratic form of X, with Q as a weight function, you can see, as a quadratic form matrix. This is the same, but in terms of U. Q and R would have to be positive definite, for this to be meaningful. Because if, for example, if this number can be negative, then there will be some X and U that can actually make the cost go down, which is not something that makes a lot of sense, because the system will just plunge into this direction then. So if we want to stabilize the origin, we want Q and R to be positive definite, okay? We want them to be positive definite. In fact, Q can be positive semi-definite, so it can be equal to, some of eigenvalues of Q can be equal to 0 if there are some states for which we don't care at all. So there are some states whose, or combination of states, whose going to 0 is of no consequence to us. However, R always have to be positive definite, and this makes sense because as long as we allow R to be positive semi-definite even, so there are some control components which we do not care how much we use. So we're not going to punish the system for using more control. The answer will be infinity. The system would say, okay, let me use infinitely high control in this direction, so I achieve some marginal gain in some other direction, because I'm not punished by using as much of these controls as I want. This makes no engineering sense. So R would have to be positive definite, not semi-definite. And you will see in the derivation later, it would play a role. Okay, so this instantaneous cost, the interpretation, as I alluded already, is kind of like this. You say, okay, here I punish X for being away from the origin, but I punish it in different directions differently. So Q would be a quadratic function, positive definite. So it would define in which direction the punishment is higher, in which direction the punishment is lower. You can recognize this as an ellipsoid, so you can say that this is, this is the equation of an ellipsoid, and there will be like principal direction in which the punishment is the highest, then another principal direction in which the punishment is the lowest. There are many ways to think about it, but yeah. You can also do like eigen decomposition on it to identify eigenvalues, and this would also yield to you where the punishment is the highest, etc. But yeah, if you choose Q, for example, to be diagonal, then your coefficients on your diagonal would directly imply which of the components of X is being punished how. Okay, so if Q is a diagonal, it will become a sum of X1 squared times Q1 plus X2 squared times Q2, and so on and so forth. So this is not anything too strange. Same here. If R is diagonal, then you would have just U1 squared times R1 plus U2 squared times R2, etc. Okay. Now let us substitute all of this goodness into HJB. So we substitute into HJB, and this is what we get. This is our instantaneous cost. This here is our partial derivative of the optimal cost with respect to X. Okay. And this here is our F of X, so X dot. All right, so this is what we get. And ultimately, this is what we wanted to arrive at. Like, this is HJB, but for linear systems. Now we just need one more component to be able to solve this equation. That one component is this part here. So far, this looks mysterious, and we don't know what to do with it. All right, let's make next step. So we have a theorem, which I'm just giving to you as a theorem, that says for LTI with quadratic cost, optimal cost has the form X times S times X. So optimal cost is a quadratic form itself, okay, where S is the positive definite matrix. So the optimal cost is a quadratic function. And that is great because it allows us to easily do the rest of the derivations. So for example, what is the partial derivative of this function with respect to X? Or the partial derivative of this function with respect to X would be, let me write it out, let's say dj dx. And we are talking about partial derivative, not full derivative, full derivative. Even though, like, I don't have partial symbol in my keyboard, so I apologize. So we'll have X transpose times C times of X, okay, plus so this would be our okay, this would actually be our derivative with respect to X times dx dx dt, I guess, dx dt. All right. So this is how we do it. We say that partial derivative with respect to X. So this is ultimately the way what we do here. A better way to say it is this is a derivative with respect to a vector field. Okay, so we have this scalar function. We want to take a derivative of it, but this is a function of X, but X itself changes according to a vector field. So it changes with respect to time as f of X, according to the function f. Okay, so f is a vector field here. And the derivative is, this is just to say that the derivative with respect to a vector field is a partial derivative with respect to x times the vector field. Okay, so this would be a better way to discuss this than to say, what I've written here, I guess. Yep. All right. Now, this is just a chain rule. The derivative of a product. That's what I did. Derivative of a product, right? So it's like derivative of the a times b is derivative of a times b plus derivative of b times a. So same here. Now this part here is, and this part here, this part here is f of x, and in our case it is a x plus bu. This part here is f of x. In our case is again a x plus bu. So when we substitute here, what we get is our familiar instantaneous cost as before here, plus those new components that we just discussed. So x times c, right? Okay. Our cx from here, and our f of x in both cases. That's it. That's what we have. So nothing too difficult happens here. Here it's very easy to make a mistake with transposes and stuff like this. So this way with x dot, I recommend it because it makes it much more easier not to make a mistake. One way to make a mistake here is to just compute dj dx, okay, dj dx, and then multiply it by x dot. That is one way to make a mistake. So if you try to compute dj dx, what you would find is two vectors, one vector vertical, another horizontal. Okay. And you will sum them. I guess you would pretend as if they stay kind of like they're both vertical, I guess. And you would have something like, let's say, 2cx or 2x transpose c. And that would be, would create, like you would forget one of those two components. You will get a 2 in front of the other component. And that would just lead to, your quadratic form might be correct, but it would no longer be symmetric. The matrix no longer be symmetric. So it's easy to make a mistake by trying to apply this thinking, but instead of thinking of it as a single entity, like a derivative with respect to a vector field, you think of it as two Jacobians, Jacobian with respect to x, and Jacobian with respect to t, like separate entities that you can multiply to each other. So if you in your derivation you have a 2 and you forgot one of those components, that is probably how you did it. All right. Do you have questions about this so far? This is like mathematically, this is the most hairy part.
No.
Okay. Good. If you have questions, interrupt me at any time, because we have enough time in the lecture for that. Like the number of slides is quite small today, so don't hesitate. Okay, so this is the situation here. We have now, let me clear all of this. We have now our HJB in this form, and the rest is just algebra. The rest is just algebra. So let us do the algebra. So first of all, we open these brackets. We open these brackets. And what we do is, for example, we can collect quadratic term with u. This is the quadratic term in u. Okay. We can collect quadratic terms in x. So this is a quadratic term in X. Here, one component. Here, another component. Here, another component. Okay, so those are quadratic in quadratic form in X. And then we have mixed components. So we have component that depends on B, so on U and X. And here we have a component that depends on U and X. And this is here. So quite simple, quite simple. All right, good. Next step is to find the partial derivative of this equation with respect to U and set it to 0. Okay. So we say that this is this equation, the minimum of it with respect to U should be equal to 0. Well, let's since we know that we know that this lies at the minimum with respect to U. So if that is true, we lie at the bottom, and we can find the derivative with respect to U, and we know that the derivative is going to be equal to 0, because anything that lies at the bottom of some locally convex shape, like at the bottom of basically like at the minimum, the condition of optimality includes that the derivative is 0. So since we know that this what we are caring about is the minimum with respect to U, we can try to find derivative of this guy with respect to U and set it to 0. All right, let's do it. So let's find the derivative of this guy with respect to U. So what's going to happen is this guy will become 2U transpose R. Here, by the way, we are going to do exactly what I was warning you against above. So we're going to sum vertical and horizontal vectors. Quite interesting, quite interesting. So more correct would be to say that this is U times R plus R times U, right? But we're going to sum them anyway. So, and here again, it will be, here there is another equation. So this equation would yield us X transpose C times B, and this would yield us B times C times X. Okay. Here, all right, let me, I guess, go just a step deeper into this whole business of taking derivative of those guys. So derivative of this guy is clear, absolutely clear. So let me even get rid of this one. So derivative of this guy is clear. That is just X transpose times CB, right? What is the derivative of this guy? What is the derivative of this guy? Well, this is actually not so clear. Well, it is tempting to say that the derivative of this guy is B times C times X, right? It's tempting to say it, but that's not correct. Why? Because U here is transposed, okay? U here is transposed. So in fact, the correct way to take a derivative of a function when your argument is transposed is to transpose the function. So the correct way is to say that this, but transposed. Okay. So this is what's going to happen. That is, we are talking about partial derivatives. We are, like, remember, here we were talking about derivative with respect to a vector field. That is a different beast. Here we're talking about partial derivatives. So how can you justify it for yourself? As in, you can just look it up in Wikipedia or in calculus textbook, and you would find some table which will tell you how to take a derivative with respect to anything. But how can you justify it for yourself? Well, there is a very simple way to think about it. Like this whole thing here, and let me, I guess, clear this. So this whole thing here is a scalar. So this is just a single number, like function. Okay, scalar function. A single number, its transpose is still itself. So transposing this particular function does not change anything. So you can transpose it. So transposing it first leads us to a function. Let me write it here. Transposing it first leads us to a function x transpose c. I mean, c is symmetric, so we don't write transpose for a symmetric function, times b times u. Okay. So this will be a transpose of the original function. Great. Now, derivative of this function with respect to u is clear. It is this guy, x times c. How to open brackets with transpose, you know, right? It is you change the order in the opposite direction and you transpose everything. So b transpose cx will becomes x transpose cb. Okay. So you can think about it this way. Like there are two ways. One is if you're going to take a derivative with respect to a variable which is transposed, you transpose the outcome. Okay, that's one way. Another one is since this is a scalar, you are allowed to transpose it without changing anything. And then after you transposed it, you take a derivative, which you now know how to do. So you can clearly see that this partial derivative here and partial derivative here, they are the same. Like this is the same as this. So here, when you do this, you would also have the same thing. Derivative with respect to this u would give you u transpose r. Okay. Now derivative with respect to this u would give you let me continue writing here. Would give you r u transposed, which is the same as 2. Or you open the brackets and you get again u r. So it will be the same as u. And here you get just 2x cb. Okay. So you understand now how we take a derivative of this with respect to. That is things that were easy to make mistakes, and it involves two different ways of thinking about derivatives. Here we thought of derivatives with respect to vector field. Here we think of derivatives of scalars, which can be transposed also. All right. Now, this is the result. You can clearly see we can get rid of those tools. In fact, if we choose control policy to be or to have like 1/2 somewhere, we might have gotten rid of those guys in the derivation, but doesn't matter. Like they cancel. Next, what you do is you take this part here, transfer to the right-hand side with the minus sign. Okay. You transfer to the right-hand side, you get a minus sign. And then you multiply. Yeah, here, okay, let me, I guess, not skip steps. The first important step is to transpose this whole thing again. Because u and x are transposed, so it would be nice to transpose them back. So it will be ru plus b transpose cx, okay, equal to 0. That is the first step. Okay. And after you cancel the 2's, okay, you cancel those. Okay, that's what you get. Next, you transfer this guy to the right-hand side with a minus sign. Okay. And then you multiply both sides by R, R inverse. So multiply both sides by R inverse. So basically just express U out of this equation alone. But what you do is you remember to transpose it. You have to do it. All right. So this is how you get this control law. Now, this control law is optimal. Okay. So this is optimal control law. You can already use it. The only downside is that you don't know what S is. Like R, you chose it yourself. That is your cost function. B is your control matrix. You know it, it comes from your system. S, you don't know what it is. You have to find it. Is the optimal cost, quadratic cost function. You don't know what it is. Okay, okay. Now, this is the control law. So we could, using this control law, instantly say that this is a control gain. So we can rewrite it as like this, where K would be equal to R inverse, B transpose, C. So people sometimes like to give it interpretations. One interpretation is, for example, to say the control law somehow takes X, transforms it in accordance to the optimal cost to go. Okay. So if the optimal cost has deformation to be taken into account here, then it transforms it in accordance to the control matrix, so control authorities you have. And then finally it takes into account the control cost. Okay. So this is like a series of linear transformations that somehow take into account your final cost, how it's going to look like your control authority and your cost of your actions. But yeah, I'm not sure if this makes it more clear to me. But if you want, you can spend time to think about like algebraic implications of this formula. But this is a standard formula. So this would be your standard LQR control law. And this is a proportional control law. This is a proportional control law. Notice if you had a second order system, let's say spring damper, X would include position and velocity. So your control law in this case would be based on position and velocity. So it would be linear with respect to position, linear with respect to velocity. For second order systems, that is what we call PD control. So this is a proof that for a linear second order system, PD control is optimal. So we for free proved that for second order linear systems, PD control is optimal. All right, that is neither here nor there. It's just something. But when people talk about PID, when they say like PID is good, etc., you can see that some of the justification comes from the fact that in fact PD component is already optimal for linear system, and PID control is usually used for motors, which are indeed linear second order systems. Sometimes first order, sometimes second order, sometimes third order. So there is there are variations, but if we're talking second order systems, then you can already see this proves optimality of PD control. I component in control law, that is just for your information, I guess. You can prove its necessity by considering something called disturbance observer. We'll understand this maybe a little later at the last lectures of the course, which takes into account also external disturbances or errors, etc., model errors. All right, so there is a connection between this and PID in terms of theoretical proofs. Okay, now this control law is called Linear-Quadratic Regulator, LQR. This is called Linear-Quadratic Regulator. If you use this control law, you're using LQR. You're using a Linear-Quadratic Regulator. Okay. Now, how do we find S? It's all fun, but before we know S, we cannot use LQR. We need to find S. Now, what we can do is we can go back to this equation, and we can substitute the controllers that we found into here, 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 and here. Okay? So we found the control law. Remember, it is minus R inverse B transpose CX. So we will get here X transpose R inverse B C. Oh, sorry, what I'm talking about. No, sorry, it will be X transpose C B R inverse times R inverse B transpose CX. Here it will be again minus R inverse, so we'll have minus sign here. We have minus R inverse B transpose CX. Here it will be X transpose C B R inverse, etc. So all of this with the will substituted will be bigger. Let's look at this. So I will try to highlight where we substituted the control, our control law. Here is the first instance. Here's second instance. Here is, I believe, the third instance. Here, I believe, the last instance. So we substitute our control law. We got a few extra minus signs here because control law is negative, has a negative sign. And so this is what we get. Now, let me simplify. There is something to simplify here. Like this is identity. This is identity, for example. And by the way, we notice now why we wanted R to be positive definite rather than semi-definite. If it was semi-definite, it could have 0 eigenvalues, so it could have been not invertible. But with R being positive definite, it is always invertible, so we always have R inverse. That allows us to find control law. So it wouldn't be even possible without R being invertible. All right, so we have now this guy. Now let us notice that we have 3 identical expressions. One expression here, X, S, B, R inverse, B transpose, CX. Another one here with a minus sign, X, C, B, R inverse, B transpose, CX. And another one here, X transpose, C, B, R inverse, B transpose, CX. Okay. 3 identical expressions. So when we sum them, we'll have only one left here with a minus sign, because we have one with a plus sign, 2 with a minus sign. They're identical, so we like to cancel each other. They have only one remaining. Everything else that remains is this quadratic form with respect to x. Okay. This is also now notice all of this is a quadratic form with respect to x. So we put x out of the brackets, and that's what we get. We have Q C R A transpose C minus CB R inverse B transpose C. Okay. So we have this guy here. And this would hold only if this for all x, only if this equation is equal to 0. Okay. So it's not a question of it having a 0 eigenvalue or 2. It is a question of this whole matrix being identically equal to 0. So this whole matrix has to identically be equal to 0. Yeah. So just to reiterate, this mean over U now goes away because we substitute optimal control law. But we still are equal to 0, as you remember from the Hamilton-Jacobi-Bellman equation. So this still rests. This still rests, and this still rests. Okay, so what we achieved here is called algebraic Riccati equation. This is called algebraic Riccati equation. One of the keystones for a number of areas, but in particular for optimal control, also used in, at least used to be important for convex optimization. And you can think of it as just an important mathematical object. So this is called algebraic Riccati equation. What we can notice here is that algebraic Riccati equation is quadratic with respect to S, with linear components here. So it has linear components here, but also a quadratic component here. So this would prevent us from being able to solve it using linear algebra. So in fact, this equation is usually solved numerically. We don't usually solve it using linear algebra. And there exist very robust algorithms that solve this equation. So this equation, algebraic Riccati equation, is what we solve to get S. And once we solve it, we substitute it into our control law here. We find K as R inverse BC. Yes. And that's how we do LQR. Now, how do we do it in practice? In practice, it is painfully simple. So in practice, if you're using MATLAB, you can call a function LQR of A, B, Q, R. This is for your linear systems. So this is your state matrix, control cost, state cost, control cost. And this will give you your optimal gain. So K, which is equal to equal to R inverse B transpose C. This will be your C. Sorry, S will be your S. And this will be eigenvalues of your closed loop system. Okay. If you're using Python, what you can do is you can call SciPy linear solve continuous array. Array is algebraic Riccati equation. As you can see, it's again state matrix, state cost, control cost. And this now is your solution to your Riccati equation. So this is quadratic form of the optimal control cost. Notice that you have to substitute it yourself into K to get to get your K, you have to do R inverse times B transpose times C. So in Python, you don't get K, you get S. So you have to find K yourself. It's trivial, is just remember to do it. Students forget about this. So if you want more robotics-oriented difficult software, this Drake a few years ago used to be one of the more exciting libraries out there. We have more competition now, I guess, but it still remains one of the more impressive robotics toolkits. Is developed in MIT by Rusty Drake and his team. So they have in one of the releases, the ones that we worked with, they have a function Linear-Quadratic Regulator, which takes again state matrix, control matrix, state cost, control cost, and it returns your optimal gain and cost to go. So that's form of the optimal cost. Now, what do we see here? What we see here is that in practice, you just call a single function. Let's say this one. Or since you're using Python, let's say call this function. And you get your solution to Riccati equation. So you get your S. And then you'll find your K and you're done. So it's kind of the same as using place. It just gives you optimal cost. But the plus side is okay. I'll discuss plus sides and minus sides on the next slide. Okay. So it's very simple. to calling place in MATLAB or Python. Place meaning pole placement. Okay, so LQR for us comes down to using software which computes a solution to the Riccati equation. But this whole charade that we did, like all of this from here to here, it was useful. So let me just, before we continue on, let me just quickly explain. Like Hamilton-Jacobi-Bellman is useful outside of LQR. It's just important piece of mathematics. And it is true for nonlinear systems as well. So it's not just linear systems, it is true for nonlinear systems as well. Okay. So if your system becomes nonlinear, but you can still solve Hamilton-Jacobi-Bellman, great, you're in luck. So it's important to keep it in mind. If you are only working with this type of Hamilton-Jacobi-Bellman, you are instantly limiting yourself only to the systems for which you have this equation. So in this case, LTI. But you can instantly imagine maybe you would have LTV systems. Maybe you would have systems with some small nonlinearity or anything else. As in, there can be a number of options. And if you can derive this equation from HJB, or from this equation essentially, then you'll be able to stay flexible. You'll be able to continue working with Riccati even when you see something that is not covered in the textbook that you have open in front of you. So it's important to know HJB just to be able to derive Riccati for slightly different systems. Okay. So in fact, if I add plus C here, or if I want to do trajectory tracking, let's say I want the cost that punishes not X, but X minus X star, all of this is possible with those derivations. You just, you can do it. Okay. Now, this derivation is just important, partly because, it's easy, nothing too difficult about it. And it allows you to keep your skills of taking derivatives not rusty. And when you're going to do other things like, Kalman filter, etc., knowing how this is done here might be useful for you there. So it's like, this is not difficult. So I would recommend you practicing this. Okay. Now, this is just important to know because Python expects you to know this. They don't give you K, they give you S, so you need to remember this part. And this is the Riccati equation, so if you want to understand what exactly you're solving, you need to remember this equation. And this equation, it might be difficult to memorize, but if you know the derivation, you'll be able to derive it very quickly. And if you don't remember the derivation, but if you just know the outline of the derivation, for example, if you remember this part at least, the fact that we need to cancel R inverse, you already know that R inverse is going to be the center, and the only thing that, you just need to be B transpose, you need to put them correctly, that's it. And so it's not difficult, it's not difficult. The rest will be done by just thinking about dimensions. So if you want to memorize it, knowing the derivation will allow you to easily remember the minus sign here, how to put B, R inverse, etc. So I strongly recommend you to study this as much as you can. Now, what is the comparison between this and our previous tool, pole placement? So just a few words. So pole placement has its own advantages. So it allows you to design exactly how fast the control error decays to 0. So you can decide how fast you go down into 0 territory, because you place eigenvalues essentially of the system. And you can design control without oscillations, for example. So you can decide if your control needs to have oscillations or not. You can decide, okay, no oscillations. That is a plus side. The minus side is it may easily require unreasonably high control gains. So I may ask, please make sure that this eigenvalue goes is equal to -2. And you need control gain 10,000 for that. So in practice, it is useless. You'll be like, hey, -2 doesn't work because 10,000 control gain. Let me ask for -1. And they'll tell you, okay, this is 1,000. You'll be like, okay, still not acceptable. And so on. So what I'm trying to say is it's very easy with a pole placement to ask for something unreasonable because you don't understand how dynamics works and you don't care about how it works. You simply ask it, now make it work this way. Okay. Let's say you have a car and you ask it to behave like a bike. You ask it to be able to, let's say you have like a better example. You have a bus, and you ask it to behave like a sport car. You're saying, okay, accelerate this fast, decelerate this fast, etc. That is like a metaphor, not analogy, but yeah, you like accelerate this far, decelerate this far, and so on, this fast. That's just not how you design a control system for a bus. It's just not a good way to do it because you would overtax your motors and so on. So in fact, very easy to go wrong. The whole idea of pole placement is that you don't really care about the dynamics beforehand. You just force it to behave the way you want to behave. And you can imagine this is not good. Now, LQR is very easy to produce good gains. Like if you just choose Q equal to identity, R equal to identity, most likely you'll produce a reasonable K. Okay. So LQR doesn't force anything on your system. And as long as your control gains are reasonable, cost is reasonable, you'll find optimal control policy with respect to this cost, which would be reasonable. Of course, here you can instantly see one downside. We're talking about optimality, right? We're talking about optimal control policy. But the cost, like Q and R functions, we don't really know how to choose them. As in, it would be good if someone told us what cost should be like. But no one is going to tell us. So we have to choose the optimal cost. And the optimal cost is not something you can look up or do anything else. In fact, you would have to just come up with it. And often enough, the performance that we really care about comes in the form of eigenvalues, not cost. So in fact, pole placement somehow deals more directly with what we care about, with eigenvalues. And LQR steps away, deals with the cost, which we don't really care about so much. So that is a downside. For example, it can easily produce slowly decaying control error with oscillations. So if you use LQR, it's very easy to get performance which is not very good. Okay. So both of them have advantage. Pole placement gives you exactly what you want to have, but you can easily ask for something bad. LQR usually gives you something good, but it's not often giving you what you really care about. So performance it can be jeopardized. All right. So this, I think, is all I want to say about LQR. Do you have questions?
No.
Okay.
It's good.
Okay. Today we will have, I believe, with Simeon, you will have a bit of a study of a discrete case for the LQR. So that will be covered. Make sure you attend the seminar. All right. We will see each other next week. Good luck.
Bye.
Goodbye.
Bye.